So in the last video, we considered a first-order linear difference equation. In this video, we'll again be going through the lecture notes from the last video a little bit more slowly, and we'll try to make things a little bit more concrete and provide a little bit more intuition. So again, we're considering a first-order linear difference equation in the standard form. So we have x sub t plus 1 is equal to a sub t times x sub t plus b sub t. So now, if we're given some initial condition x naught, so if we know the value for x naught, well, this has a unique solution, and this is fairly easy to see. All we have to do is, well, we start with x naught, well, and we know that x1 is equal to a1 x1, a naught x naught plus b naught. And of course, we know that x2, oh, sorry, I lost my 1 there. Let me put that back. So, we know that x2 is going to be equal to a1 x1 plus b1, x3 is going to be equal to a2 x2 plus b2, and so on, all the way until we get the summation. And it's pretty easy to see the pattern of the summation by just substituting in each of our x1s and x2s into the next recurrence relation. So in this particular case, we substitute in x1 for that, so we get a1 times a naught x naught plus b naught plus b1, which is then equal to a1 a naught x naught plus a1 b naught plus b1. And plugging it into this next one, what we get is a2 times all of x2, which is going to be a1 a naught x naught plus a1 b naught plus b1, all that plus b2, which is then going to be equal to a2 times a1 times a naught x naught plus a2 times a1 b naught plus a2 times b1 plus b2. And you'll see it's pretty straightforward to see that each of these terms corresponds. So that goes to that term, and our b2 here, well, in each one we're left over with 1 at the end. That goes there. And let me use a different color here for this summation term. Goes to that there. Okay, and as I said in the last video, this is a little bit ugly, but when a and b are constants, this is actually really simple, and it's just a geometric series. So we have that xt, if we set those to be constants, we have that xt plus 1 is equal to axt plus b. And plugging that into the formula we have above, we find that xt plus 1 is equal to a to the t plus 1 times x naught plus b times the summation from I equals 0 to t of a to the I. Now, if a is not equal to 1, this is just a simple geometric series, and this entire thing, this thing here, is equal to that. So you can, that's just a simple geometric series. You can multiply it out if you don't believe it. Of course, this only works if a is not equal to 1. If a is equal to 1, well, then this denominator here becomes infinity, and so it doesn't work out. Luckily, it's pretty easy to see that if a is equal to 1, well, then this term here just turns into t, and so then you end up with just t plus 1, since that starts from 0 all the way to t, and you end up with this t plus 1 times b, and of course, since a is equal to 1, this thing goes to 1, and so this term goes there. Okay, so in the case of a first-order linear difference equation with constant coefficients, you can actually just explicitly solve for it by plugging things in. And then you know this geometric series, and that has a nice closed-form solution. Unfortunately, things don't always have as nice of a closed-form solution, and just iteratively plugging things in doesn't always work out like this. And so for more complicated problems, especially higher order problems, we need to turn to other techniques. And one of the principal tools we use is something called the principle of superposition. This is used all the time for linear difference equations, and was also something we used for linear differential equations back in MATC58. And let's go ahead and prove that the principle of superposition for the simple case of a first-order linear differential equation. So here we have our homogeneous solution. So this is our homogeneous solution. And it satisfies the homogeneous equation. So we set b equal to 0. So here b is equal to 0. And here we have a particular solution, x sub pt. And here we have our b here, which is not equal to 0. And then all we have to do is, then our claim is that if we add the two together, that satisfies x sub t plus 1. That satisfies the, that also satisfies the actual first order linear difference equation. And that's by linearity. The proof here is really simple. So let's go ahead and give a proof. So, well, x sub t plus 1 is equal to x sub h comma t plus 1 plus x sub h comma, x sub p comma t plus 1. And you can just plug each of these in. So this here is equal to, we know that these two things up here are both satisfied, and therefore that is equal to, let's see, this is a x sub h comma t plus a p sub t, a x sub p comma t plus b. But of course, then we can collect together these terms, and this is equal to a times x h comma t plus x p comma t plus b, which is equal to a times x sub t plus b. And the key step of this proof is just that we can break up everything and just sum together different parts. And that is because that's precisely because we're working with linear difference equations, just as in the principle of superposition for linear differential equations. Okay, so now that we have that, we can go on to use another technique from linear differential equations, so the method of undetermined coefficients. Again, we already knew that a solution for the homogeneous equation, that was from last lecture. And what we need to do is we need to find a particular solution. Now, how do we guess this particular solution? We use the same vague sort of technique that we used for the differential equations, where we look at the form of the b. So here we know that b is constant. And so since b is constant, one reasonable guess is that there is some constant particular solution to the non-homogeneous equation. And indeed, when we set the guess of some constant k, we end up with, let me write that out. So guessing that x sub p is equal to k, we plug that in, and we end up getting k is equal to ak plus b, which you can rewrite as k is equal to b over a minus 1. And the same goes for when a is equal to 1, that's a little bit more complicated. Well, what happens when a equals to 1? Why does it not work? Well, let's actually plug that in and see that it doesn't work, rather than just taking my word for it. So suppose we guessed xp is equal to k. Well, what goes wrong here? When you plug that in, you end up getting that k is equal to ak plus b. But a is equal to 1, so this implies that 0 is equal to b, which is a contradiction if b is not equal to 0. The reason that this doesn't work is that k constants, so xp equal to k, is a solution to the homogeneous equation. And so we can't use it as a solution for the particular equation, since we know that it's only a solution when b is equal to 0, and we care about when b is not equal to 0. So instead, we use this guess that it's some polynomial tk, and it's some constant times t, it turns out that, of course, since we know that we don't have to use this particular guess, there are other guesses that would work. For example, since a constant is a solution to the homogeneous equation, we could have also guessed xp is equal to tk plus 5. And that would probably also have worked. In fact, we can do it for any constant. That's the whole point of the principle of superposition. But it's easiest for us to just guess a tk where k is constant without having another constant term added to it. And when we do that, we get that k is equal to b, which allows us to do these substitutions to get the general solution. Okay, so now let's move on to the last technique, which is cobwebbing. This is just a fancy way of saying we're going to plug everything in and graph it out. Let's try this with a relatively simple example. So basically what we're doing is we're starting with let's start graphing. So we have the x, we are going to plot out the y equals x line. So this is the y equal x line. And let's suppose that f of x is something really simple. Let's say that f of x is equal to, let's say, 1/2 x plus 5. So this is going to be 1, 2, 3, 4, 5, starting there. So this is at 5. And let's say this is also, that means this is also at 5. And we're going to say, let's say this here is 10. And 1, 2, 3, 4, 5. Let's say this here is 10. Let me actually extend this out a little bit. Oh, sorry, messed up that. Let's say that's 10, and oh, I should have drawn that line a little bit better. Let's say, okay, that works. And then this line goes there. And all we're doing with cobwebbing, let me actually decrease that a little bit, is we're going to start at some initial condition. Let's say that we're starting at some x naught here. And we're starting at the point x naught 0. So that's this point right here. Let me do that in purple. And the first thing we're going to do is we're going to set b. So the second coordinate, so this here is the, let's say this is the a-axis, and this is the b-axis. The first thing we're going to do is we're going to go up to x naught f of a. Well, what actually is f of a? So when we plug in f of a, that's precisely this graph here. And so all we have to do is we go up from this point up here, and then we follow along in the next direction. So we set a equal to b, and so we just go to the line y equals x. So then we go here, and then we repeat that over and over and over again until we get tired. And so it turns out that these sorts of drawings tend to look a little bit like cobwebs, especially for certain types of nonlinear difference equations, which is where the name comes from. Often it is easier to use a computer program to draw this out, and so we'll be seeing an example of how to do this in Python in the next video. But the basic idea here is we can illustrate the behavior of this first-order system. So we see that we start here at this point x naught, and then x1 is actually going to be right here. So we're going to go here to x1, and then to x2. So x1, x2, x3, x4, etc. So we can see those plotted out as we go along. And we also see that the difference between x naught and x1, the xi and xi plus 1 decreases as time goes on, at least in this particular set of initial conditions. Obviously, this is a little bit silly for a simple linear equation because each time you're just going in the same direction. But when our f of x graph is a little bit more complicated, this method can be helpful in illustrating what's going on. So stay tuned for the next video where we'll discuss how to, we'll show you how to generate these sorts of cobwebbing graphs via Python.